special episode of Voice of the Sea, we join over 6,000 students and community members at SOEST Open House, exploring the research, innovation, and education opportunities available at the School of Ocean and Earth Science and Technology at the University of Hawaii at Mānoa. Every 2 years, during SOEST Open House, faculty, students, and staff share their research and love of science with students and the community. First, we take a look at atmospheric scientist Zachary Menzo's demonstration of the ideal gas law.
This one is the ideal gas law. This tells us that the temperature of a liquid affects its size. So I just poured some water in this can, and now I'm going to put it on this burner and start to heat it up. So I'm going to increase the temperature. That means the size of the liquid is going to get bigger on the inside of the can, and then in a few moments I'm going to put in this ice cold water. So it's going to go from big, big, big to small all of a sudden, crushing the can as a result. Right now it's hot, it's very big, it's going to be cold, it's going to get small really fast. Okay, you guys ready? This one in, ready? 3, 2, 1. Woo!
We have 2 pools here with a lot of ice. We took 40 gallons of ice and we broke it up into chunks. And in this pool, we have floating icebergs. And in the pool over there with the polar bears, that's like Greenland with an ice sheet up on land. Every half hour, the kids are taking a measurement and we're putting them up on the charts behind me. And what we've seen so far in this pool with the floating icebergs, the water level stayed the same. But our Greenland pool, as the ice melts, the water level's coming up. This is our iceberg pool. You can see it's all floating, just like ice cubes in a glass.
Right.
But over here, the ice is up on land, just like a big glacier, an ice sheet, just like Greenland. And we've been tracking it over here all day, and you can see how fast it's going up.
Oh, wow. You're going to run out of graph room.
We might, and it could tip over, just like sea level rise. We have tide gauges all over the world, and we measure the ocean surface level, and then we produce data products to track sea level rise and ocean variability.
We're sharing the Hawaii Sea Level Rise Viewer, which is an online mapping tool to model different effects of sea level rise, including high tide flooding, flooding from increased wave run-up on our shoreline, and coastal erosion. We have a lot of problems with beach erosion on a lot of our islands, beaches disappearing in front of seawalls, big condo buildings on Maui getting affected, beach loss in Waikiki, Sunset Beach. People see these impacts happening today, and we get questions, well, how much worse is this going to get in the future? This data is an attempt to look at a range of scenarios of what's at risk in the future. Right now we're showing the sea level rise exposure area, which is an overall footprint of erosion, high tide flooding, and wave run-up flooding. You can zoom in and out. You can go to all the different islands. Here's Kauai. You know, we could zoom in on Kapa'a as an example. So this data is available for our communities all over the state for the different islands.
What kinds of degrees are the students in SOEST working toward?
Many different degrees. So SOEST as undergrads there's atmospheric science, there's earth sciences, there's global environmental science, and there's earth and environmental science. SOEST has a lot of hard sciences, and hard sciences have a lot of math, have a lot of physics, have a lot of chemistry. So those classes are very, very difficult for a lot of our ILA mentees. We have these grad students that have gone through it. They know exactly what to expect, so they can mentor them really well.
What does a mentorship provide?
We pair up our mentors with mentees. It's kind of like a matchmaking game. We pair them up based off of their interests, and then all they really have to do is get together once a month and hang out and chat. It doesn't even have to be academic. Even though our program is SOEST Maile Mentoring Bridge, we don't just mentor them on SOEST curriculum. We mentor them on being a student in SOEST, which incorporates everything from your personal life to your academic life.
Were you in the Miley mentoring program as an undergraduate?
Yes, I was. I was going through a really, really difficult time in SOEST. I was very, very close to dropping out. Having that person who was like a peer and less of a professor to mentor me was key in getting me through SOEST.
Tell me a little bit about CMOR and what the acronym stands for.
We're the Center for Microbial Oceanography, Research and Education. Our focus then is on microbial oceanography and kind of unveiling both the microbes in the sea, what kind are there, what they're doing, and how you can extrapolate up from that to say things about global element cycling. So right here we have resources for teachers and educators that have pre-made labs with slides, tests, quizzes, everything like that, just to kind of help schools incorporate science into their curriculums a little more readily. The beautiful thing about oceanography is it's a marriage of modern technology and then ancient practices. Like, we've been a seafaring people for a very long time, and it's really kind of beautiful to see those two things come together.
So what we're going to do here today is recreate this earthquake that happened in Lenei and see if we can alert ourselves to what might be coming here in Honolulu. Ready? Time zero. Rumble, 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 rumble,
Just
rumble.
nice and slow,
Time 2
slow,
seconds.
slow.
4 seconds. 6 seconds. Group A, get ready. Here we go.
Let's go.
8
Okay,
seconds.
shake, shake,
Go.
shake.
Group A, shake.
Where's Kihei?
Good job.
Let's go, Kihei.
9 seconds.
Let's go, Kapalua. Start shaking.
Kahului, say
Yeah,
shake.
we go.
Here we go.
Oh, yes. We got
Good
it.
job, guys. 35 seconds. Drop, cover, and hold on. The earthquake is hitting UH Manoa right now.
You guys are in HIGP, you guys are on the 5th floor where we have the planetary science. Oh, back here we have the thermal cameras where we're showing the different things that we do with the thermal cameras, and we can show kids, you know, that a little bit of like the heat, but we can also teach them about things like what we call thermal inertia, basically how these rocks can heat up and cool, and how fast they can heat up and cool based on like the size of the rocks. We also have a lot of meteorites, rocks that came from space, that came through the Earth's atmosphere and landed, so we're looking at that. NASA also loaned some moon rocks for us so that these kids can enjoy and look at these moon rocks as well. We have a lot of images that came back from NASA missions that we are also displaying. We have what we call a Magic Planet, where we can project maps and images onto a sphere. But we also have a lot of rocketry stuff as well, where we show kids some of the things that we've launched, as well as understanding of what it's like to explore space and how we explore space.
And what's so great about studying space here at SOEST?
Here in SOEST, as well as in HIGP, we have produced some of the most amazing planetary scientists in the world, and it's great to be part of that and to work with these people.
The University of Hawaii Sea Grant College Program, helping coastal communities of Hawaii and the Pacific through research, education, and outreach. Serving the community, from elementary to graduate students. Hawaii Sea Grant.
Welcome back. We're at the 2019 SOEST Open House, checking out more exhibits.
Its name is Kamakai.
It's not helping that much. That one helps more.
My specialty right now is on the electric grid. Looking at how can we integrate more renewable energy onto the electric grid. Of course, that's very important in Hawaii. We have a mandate to get to 100% renewable energy in 2045, and there's a lot of technical issues of how to do that. We dig into a lot of the science and engineering behind that. We involve modeling and simulation to figure out what the effects of larger amounts of penetration are going to be, maybe the balance between wind and solar, how much is economic to include batteries as energy storage. We get into controlling PV inverters to do certain functions for the grid to support the grid. We get into monitoring and analysis of the grid's operation. We've developed some devices that help us gather data from the electric grid and analyze it.
And so what is it about your work that your lab is trying to show the students today?
They're generating some power by cranking a crank, and we're seeing, well, two main themes. One is that as they let up with the cranking, then the lights dim, right? And they need to balance themselves between the loads and the generation. And it's kind of that's simulating what the electric grid has to do, the utility has to do to maintain the very constant power that we're accustomed to in our homes. And the other theme that we're sort of demonstrating here is the students have a bigger crank that they're cranking, they're generating power that actually is lighting up light bulbs. We have two different types of light bulbs, the LED light bulbs, which are much more efficient than the traditional incandescent, and it's really big difference that you can feel physically. Like the students are just barely able to get the incandescent to even start to light up, whereas the other one is pretty much going full steam.
Nick, can you tell me a little bit about the work that you do?
Here at UH, I'm in the Ocean and Resource Engineering Department, specifically doing ocean resources. So I study wave energy, how we can use wave energy for things such as ocean exploration, ocean science, as well as for other purposes such as security and things of that sort. I work on a device that recharges offshore vehicles, things such as underwater drones, as well as I work on a project to use wave energy to desalinate water for emergency disaster relief.
Can you talk me through some of the other things that maybe you're using the wave tank to teach today?
We're teaching a lot of the processes that happen near shore here. One of my favorite beaches to go to as a kid was Bellows. And so I'd go into the water at Bellows, and you know when you're walking in and all of a sudden it gets super deep and you're like, whoa. But then you see other people and it seems that it's only ankle deep a little bit further out. What's happening? Why is that? This wave tank is perfect for showing that because as the waves come, they crash and they scrape sand away and they pile it up into a little sandbar, which you can kind of see right here.
Yeah.
And so it happens multiple times. As you're walking out, it gets deep and then it shallows back out. And this is a perfect example for someone who just earlier today was like, oh, I'm going to Waimanalo. And I was like, this is what you're going to see. And they go there all the time and they just never understood why that happened. This, you can actually see it from the side. Additionally, we're showing things such as how ocean plastics end up on shore. You have your rubber ducky on the top here, and it moves closer to shore. But the other one is moving the exact opposite direction.
Oh, that's so cool.
So you can actually see the undertow happening right here. We've had some people actually from the civil engineering department come and ask us questions on like what happens when you have a structure. We'll take the paddle and we'll show when you put a wall in what happens with erosion and things of that sort.
Oh, can we do that?
Yeah. So imagine that this is your seawall, and we're going and we're putting it into the sand here. As the waves come, they'll go and crash up against it, and if your seawall isn't designed well, it will start to scrape away and scour. And so if you squat down, you can kind of see a little divot forming.
Yep.
And over time, this will scrape away. So it'll retain all the sand on one side, but not on the other. Mm-hmm. And now you've lost a lot of what was supporting this wall, and it'll fall over. So it's really cool. We have a couple of wave tanks like this, and part of our lab here, we look at different types of structures that, when you design them correctly, they don't cause these effects. And how can we make it so that we're engineering ocean structures to be better for our environment?
We have here a model of the large-scale circulation in the subtropical gyre. So we're going to use some little pieces of plastic to trace the currents. We'll use some dye to show how the water moves. So we'll put some in the middle and some on the east and some on the west. The dye in the middle is not moving very fast, not really going anywhere. A little more on the east, but on the west side, notice how rapidly the dye has moved up to the north. So that is equivalent to the Kuroshio in the Pacific or to the Gulf Stream in the Atlantic. And now they are all clumped together. And that clumping, that convergence of the flow near the surface is what gives us our Great Pacific Garbage Patch over here.
We are looking for a few heroes, mentors, trailblazers, innovators, a passion to change lives, spark curiosity, open hearts, and awaken minds, help students answer the question, who am I? This could be your calling, but this is no job. It's the journey of a lifetime. Be a hero. Be a teacher.
We're at the 2019 SOEST Open House with Sea Grant Extension Agent Palika Andrade.
Palika, so this is your Nakilo'aina project.
It's part of our Nakilo'aina project, yeah.
Can you tell me what you're trying to show today?
Okay, so just Nakilo'aina, just broader, just trying to build communities of conscious watchers. We wanted to introduce our community, our kids, to the intertidal zone as one of the roughest places to be, right? But the coolest place to be because it's where most of our kids meet the ocean. We just brought some opihi because opihi, that's what we love here in Hawaii, right? And that's kind of what they're gonna see when they get to a rocky shoreline. We do a lot of research on the intertidal on other parts of our project, the Nakilo'aina. We're looking at intertidal productivity of the opihi fishery. What we did was we picked 10 opihi within every species across size classes. We measured the length, the width, the height, weighed the whole animal, took the animal out, weighed the animal by itself, dissected out the gonad, weighed the gonad, and sexed the gonad. So the gonads look green if they're females and like a creamy yellowish if they're males. Some of our researchers are finding hermaphrodites, so the ability to go both ways. The bigger the opihi and the more mature the opihi, the better the quality of egg is. So we can give you a better idea of not only the capacity of spawning, but at what sizes and what ages they would give us the best quality egg. Our intent, a lot of Nakilo'aina's intent is how do we understand productivity so we can continually eat from our shoreline. Cultural practice wasn't about us eating opihi. It was the ability for us to eat opihi over generations. How do we understand the productivity so we can continue the traditional practice of allowing our future generations to have productive landscapes? So let's just say that this is your stable pink zone and stable habitat. And this is summer, yeah? This is big limu. They don't eat this, but they can keep it back. So they're grazing and they're just keeping it back so this doesn't get bigger and bigger. But let's just say these four are needed to keep this mode. When you take one away, now limu starts to encroach, right? And so they're just trying to keep this back. So when another harvester comes and takes one more, this starts to encroach even more. And then you take one more, and this starts to encroach. And so there's just one just kind of doing this, and then this goes over. So this guy is just trying to keep that down, and then you have this. Once this sets in, our assumptions, and this is what we're testing is, this is hard to get rid of again. And this is the danger of overharvesting. Not that there's no seed in the water, but that there's no habitat to attach to. So I think that's what happened on Oahu. There's plenty of seed in the water, but because there's no habitat to attach to, we aren't able to bring that population. So on Oahu, you can put in a management and say absolutely no picking. And you won't bring back as quickly the populations because there's no habitat. But if we go in there, and this is the experiment, and you help to reset the habitat, and you go in and like on a really dry, the October, November months when it's drier and everything's dying back, and you go and help it along, put some hot uke because they're competitors as well, but they're grazers to help start to clean it. You open up more ground for seeding to happen, and then you can start to reset. But then you have to put in the rest to make sure that they can keep up. And then when you hit that nice carrying capacity and understand it, you can start to, you know, if we have 4 here and you potentially take 1 out, 3 more will settle in. Yeah? And then the next year, these 3 are a little bit bigger, and you can possibly maybe take 1 of these, and then more will settle in. And then you can start, and that's productivity.
Hi, my name is Ángeles Gallego. We're here today to show you how the ocean acidification is affecting our corals and our ocean, and why is the ocean acidification happening. We have here 2 jars with corals, and in this one we're gonna put some water, and in this other one we're gonna put some vinegar, right? Okay. And the vinegar, you know, is very acidic. Now we're gonna put this, is a pH indicator. It's a liquid that tells you how acidic is a liquid. So when it's green, it's normal, it's basic, but when it's red, it's very acidic.
Just like what you might do in a swimming pool to test.
Exactly, they use it for fish tanks to know what's the pH, right? Or in a swimming pool.
Oh my gosh, it's bubbling in there.
Right. So this one, we're gonna put this, and it got green, right? Because it's normal water. It went very dark. But in this one, now we have vinegar, right? So we're gonna put the same liquid, and it gets red, because it's very acidic, yeah? But also, can you see what's happening to the corals here?
I think they're dissolving.
Right, can you see there are tiny bubbles coming out? Yeah? This one doesn't have the bubbles. And the bubbles mean that the coral, when it's acidic, the coral is getting dissolved, it's getting destroyed, right? So that's what happened when the water is acidic.
So if we left it in there, it might actually, we could come back and there'd be no coral
Exactly.
left.
In 1 month, you could see this, and it's gonna be all like sand, like all destroyed. This is what's happening now in the ocean. So here we have our normal water, right? That is green, because it's normal. So here we have more water. I'm gonna put some of these. So all the gases from the car are gonna come through this hose into the water. Okay, Toby, ready? So Toby's gonna start the car. And now you see, as you mentioned, it's turning it kind of yellowish, orange.
That was quick.
It happens super fast. So the gases come, they interact with the water, and immediately you get this reaction where the water becomes orange, right? Acidic.
And so how does this demonstration relate to your research?
I use computational models to see how the ocean is going to be in the future. So by, for example, 2100. So we see in the models project that the pH or the acidity level of the ocean is going to increase, and to hopefully get those results to policymakers, and that they can evaluate which policies would be better for avoiding these problems. And people like me, like we came to United States to study, to do my PhD, and hopefully I go back to Chile and I can help my community or the people there.
SOEST is a world-class research and academic institution with 4 academic departments and 9 research units. Watch and learn more online at voiceofthesea.org. Follow us on social media at Voice of the Sea TV. Mahalo for watching Voice of the Sea.